I'm very happy to have been invited to this very timely conference. I'm often considered as the theory guy, and the theory guys are the ones who know everything, and that is very wrong, I'm afraid. So I should run away, first thing to do, because I will only give you questions, basically, and only hints to answers. Okay. So, who am I? I will not say much, except that I work at this wonderful Groningen institute called Cognition, Cognitive Systems and Materials Center. And this is, it's almost a neuromorphic computing institute, but it's much more a material science, and then it omits the neuro part and then goes to computing. So they are trying to develop new material-based microchip technologies that are not necessarily neuro-inspired or brain-informed, but different in some way, and doing miracles. And we are waiting still for that to happen. But anyway, so it's the materials perspective and nonlinear phenomena in physical nanoscale systems perspective that I'm, in a sense, interested in. Okay, so first of all, I want to motivate that, at least I want, a general formal theory of computing, and computing now in something, in helplessness, indicating, well, quotes. Because we don't know what computing means in general. There are several active lines of research that obviously have to do something with computing. There's the whole world of digital computing. I will not say much about that. There is the neuromorphic computing area with partly more technology-oriented, the big players with Intel, let's say, and the more brain-inspired ones, closer to computational neuroscience, with Spinnaker and Brainscale somewhere in the middle, in my feeling. And then there is this area that is mostly driving me, has no name. Some people call it immaterial or physical or unconventional or natural computing. That's where physical phenomena of all sorts in all media, chemistry, even mechanics are investigated and see what can you do with them. Among them, possibly also the strange things that happen in brains, but it's not central there. Well, these efforts or exotic attempts to understand what might happen in very complex systems if they, well, process information or compute has been investigated since 50 years in many niches under many names, and I have computed, I have not computed them, I have collected a number of those names, as you see. So it's, if you go deeper into the history, you get a dizzy feeling. And also theory approaches have been attempted many times from many angles. There's not a general agreed route to try to understand what information processing in very complex, strange systems might mean. Has been tried many times. Some of these efforts are still very active. I made a collection and tried to understand them, and you see none of them has so far made the big gaining, the overall, you could say, winning bet. No one follows any one of these completely, and for many reasons. It's a very confusing situation. The more you read stuff from many different sources, the less you think you know what to think. Okay, but today I try to convince you that there is hope and that one should aim for unified theory. Still, although history has not yet shown us a way how to do this properly. If we would have a general formal theory of computing, which would include the digital computing theory, this vast volume of textbook knowledge that we have, as a special case, but also include what the neuromorphic community is interested in, plus the optical computing and many others that are very small niches, like DNA computing or Fusarium computing, or the people that look at ant colonies and try to understand what's happening there. All of that together, is there a general view on that unites all of this? A formal, I'm a mathematician by training, so I would want to have a formal theory that where you can establish proofs for theorems that are based on concepts that are very rigorously and simply defined in axioms. If we would have that, we could, for instance, understand if I have one strange system that works with, let's say, Fusarium fungi and does something strange, and another system that works with coupled mechanical oscillators, at this moment we would not be able to understand, can they do the same jobs? Can they be related to each other? What are commonalities, or what are the different things that they can do, each of them better than the other? We have no common framework to classify, compare, and analyze different sorts of computing systems. If we would have a general theory, we could do this. Okay, so it would be, well, the paradise for theoreticians. So what would be the essential components of such a GFT, general formal theory? First of all, one has to make some robust cuts and carves and come to some elementary agreement on what we are going to study. So one thing that is halfway agreed on by very many people in this philosophy of computing and theory, abstract theory of computing domains, is that a computing system must be physical. So we are not talking about some abstract concepts that do something, but a computer, a computing system ultimately must have a physical realization, must be a machine, and it must receive input and generate output. So we are not thinking of a stone whose equations at the quantum dynamical level could implement maybe Turing machines, but a stone is not something that we would call a computing system. Because there's no reasonable way to give input to it or extract output from it. At least I don't know yet. So that's a basic assumption. But you see here there are some different computing systems. These ones you know. This one is very classical control system. It's the governor for steam engines. And this one you also know. These are different, they work apparently differently, and still we would say that these systems compute. But we would be very much challenged to say, why would we think that these are all computing systems? Because they do different things in different ways and in different relationships to time and to being entrained to the environment and the ways they get inputs and produce outputs. So also, if we ask theoreticians to describe the internal mechanisms of these systems, you will find that different traditions and different types of researchers and engineers use quite different mathematical formats to describe what's happening inside in these systems. If we want to have a formal theory of computing systems, then we must, which should also include theories about or formal descriptions of the systems, the mechanical machines that do the computing, we must somehow come to terms with the fact that there are obviously different formalisms at work and used in practice to describe the physics of these systems. Another thing that I think is very much underdeveloped and underappreciated is that we do not speak of computing just as something abstract that happens, but we use computers, now I'm speaking about normal computers, to solve practical tasks for us. A computation, input, something happens, output, is meant by the user to help him solving some external tasks. So the input-output mappings, whether they are static functions or continuous in time, they must be mappable to external task definitions. There are many different types of tasks. Oops. Let me go back. If we speak of tasks, we also speak of users. So computers only can be considered, according at least to some theoreticians in the field with whom I go along, can only be considered to be computing if someone can interpret the input and output signals that are given to it or taken from it, can be interpreted. That's already saying enough. So you must have a user, an external person, or which can be a human or a robot or a software agent, or it can be a community, or it can be in a complex computing system, other modules that listen to some other module. In general, so there's even a philosophical terminology for it, a strange one, I don't understand this, but people use this, a computational entity that looks at the computing system, interprets what it's doing, and only in this moment, when the input, physical input stuff that's given to the computer is being, you could say, encoded, and the encoding is understood, so there is something like semantics, which will become the main topic of my talk today. Only then can we speak of computation. Computation is nothing that happens just on itself. There must be a user. And the user has a mental model of the computing that's happening, of the process. The user must know what this input that's physically given to the system means. If you type something, you start from words in your brain. They somehow get into finger commands that are transformed into mechanical key presses that are then, and so forth, transformed further and further until bit patterns arise and so forth. And the user is not aware of all of this, but the user has a mental model of the input to a certain degree, at a certain abstract level of understanding. Also, the user has a similar model of the output. I'm not saying more about this to save time. And a transformation model. So the user has an idea what should happen between the input and the output, not a full specification of all the details that happen in the machine. That's not what the user normally has. But the user has minimally an implicit evaluation criterion to say, okay, this was an okayish way to do the computation, the input to the output transformation. It can be also very detailed understanding of what's happening. For instance, in old-fashioned classical chess planning, the user, so a chess player who uses a computer to help him find the best next move, has a good understanding of, let's say, the planning hierarchy that the chess program goes through. So you can have a detailed understanding of the intermediate processing or a very abstract one. There are many types of tasks. I use only these three: controlling a physical plant as a task, which is an online sensor motor control type of task, or a classical AI task, in the history of AI, one of the most important ones, planning. like in chess game planning, or just if you just call Wikipedia, you want to get some information. That's also a task, which is in a strange way self-referential in the computing sense. There are many other tasks and other types of tasks. And we do not, in the neuromorphic community, so that's my feeling, have a good understanding of what would our neuromorphic computers be good for. So we often compare them to what the deep learning people do. Okay, so that's one way of just shrugging your shoulders and say, okay, maybe we could do this, maybe not. But if you really think these thoughts to the end, and you want to have a brain-like computing system, then it should do similar tasks that our brains do. So they should do similar tasks as your friends do, or maybe yourself. And how would you describe the tasks that you expect to do with the help of people? So these are questions that I think are not appreciated enough in the world of, you could say, more technology-oriented neuromorphic computing research. Okay, so I now slowly turn to the actual centered parts of my talk. So we speak of computing systems quite in general. We think I'm speaking about users who use such systems. The systems, on the one hand, are physical machines, like here, digital machine, physical machine, that are operated by the user. The user has also a mental model, an idea of an information processing procedure, algorithm, process, dynamical system, whatever, something that happens abstractly that should transform information. And this should be mappable to tasks in the physical world again. So I like to think of this as a sandwich, that computing as an abstract thing, an abstract concept, like in the digital world, what Turing machines can do. It's very abstract and very, you could say, platonic. And actually, if you read the original work of Turing, about the Turing machine, you will see he relates this directly back to antiquity, to Aristotle's ways, considerations about reasoning and truth. So it's all very abstract and very platonic. In the middle, and these abstract models of computing should map to physical tasks in the real world and to physical machines also in the real world. Okay, so this is the challenge to model. We need a model, or the general formal theory that I have in mind as a future project should give us a good, consistent story that binds together all of this. And in brackets, I say the digital people have this. They have a full textbook knowledge and math coverage of all of this, which allows them to specify tasks, informal logic, relate that to models, as I will show on future slides, to formal abstract models of computing processes, and map it also down to models of physical machines. And that's one, and they can even model today user attitudes, so in the sense of partly meta levels of their theory building. And my feeling is that this is part of the success story of digital computing, that they can bind together all of this in a consistent way, where everything matches everything else, and people who think about tasks can communicate and talk with people that you look at abstract concepts of computing procedures, programming languages, for instance, down to the physical level. Okay, so we want the same. At least I want the same, and I hope I live long enough to see at least the beginnings of that. It's a race against time, I must say. That's a sad. Yeah, what would you think? How many decades will it take? The young ones among you, you have a bright future. There are so many open questions and so many big discoveries can be made. So yeah, you have a good time ahead. Okay, so we want to have a theory of all of this, and this theory, that's us, at least the theoreticians, we want a model of all of this. So what does that mean? What does such a model, or one model is a bad metaphor. If we look at the digital computing people, they do not have a single model of computing machines. They have a full coverage of textbook pieces of knowledge of sub-theories, of automata theory, formal logic. They have to learn all of this in when they study computer science. A theory of computing, of computability, of complexity, a theory of compilers, programming languages. So it's a lot of things, but they are all translatable into each other, these different parts of the textbooks in consistent ways. I should say I know all of this quite well because I was teaching theoretical computer science for 20 years. And I must say I remain impressed by the rigor and beauty of this building. And I would like to have something similar for the more general neuromorphic and materials-based computing. So it's a complex situation. In other work, I have been describing parts of the actually a whole hierarchy of formalization models that are needed, I think, in the middle to cover the abstract concepts of computing in complex physical systems. I will not go into this today. Today, I want to concentrate on what happens at both sides of the sandwich when these abstract models of computing have to be related to physical tasks, you could say at the top, and to physical machines or neuromorphic substrates at the bottom. Just so if you are interested in these things, then the slides will be downloadable for you so you can check out the references. There's this brownish layer. These are the classical models that physicists would use to describe their physical systems. This is a graphical representation of the actual physical system. This bluish stuff are the models that people might use to describe tasks. I think only the digital people have such formalisms. We don't have them. And this is the actual physical, or should represent the actual physical world. Today, I want to concentrate at this part and that part and more or less ignore the middle part. So, this is a question of semantics. Well, going back. I'm a bit confused because what I see here is not exactly what I see there. So that's what I want to discuss now in the rest of the time. We have something complex in the middle. We have formal models of the hardware, or at least we have different ways of writing down formal models for hardware. physicists or neuroscientists have their own formalisms. And we may have formal models of tasks. And we need a relationship between these abstract models of computing, of processes, of information transformation, and models of hardware, and the same as above. So if you see on following slides these chains, these golden chains, these mean semantic relationships, where something abstract has to be connected to something concrete or something symbolic to something physical. Okay. The word semantics itself is very unclear. So there's one way, if you hear of semantics by philosophers, they might refer to semiotics, which is a large field that I just want to mention. It exists. It's operated or discussed in philosophy, in the arts, in architecture, in the social sciences. And it's about how actual people use symbols or words or other signaling systems or gestures to denote something in reality. This is hardly formalized, and there are several classical memes which themselves are discussed by these semiotic people. That symbols, that's the meme of semiotics, the semiotic triangle, that symbols mean reference, but the meaning must be mediated by some agent that thinks and gives meaning to this relationship and defines this. I will not go into this here because that's not what I have in mind. I have in mind a more mathematical and more, you could say, natural science inspired way of looking at semantics. Namely, something that's known in mathematics, where you have a formal system or a formalism to describe something. For instance, the formalism, that's the classical formalism to describe stuff, formal logic. So this is first order logic. There exists a thing which is a sun and shines. So that's a way to write down something. And now it should mean something. It should mean that there exists a sun that shines. So this should be the real world thing. Okay, so, and the catch is that this does not work. You cannot formally, mathematically define a link between something that's formal on the one side and reality, because reality is not formal. Reality is something we experience or do or destroy, but it's not formal. You can only have a formal link about which you can say provable theorems between two formal sides that you want to link. So this does not work. Symbols cannot mean something if the something is not formal itself. So look, how have the logicians have struggled with this, and they found a solution for this problem. Namely, they look at some formalism, like the formalism of logic, of first order logic in this case, where you can write down descriptive things like this, and then it can relate to another formalism in which you can construct something that you could say is a stand-in, a replacement for the physical world. It's a more physical mathematical formalism than that one. That is meant to be a descriptive mathematical formalism. And that is, you could say, an object math. It's a math that creates the finest grained atomic reality that mathematicians can create, and that normally is set theory. So I cannot quickly now explain you could say, the history. There's a long history behind this, actually 2,000 years of history, why this came out as a solution. But once you do this, creating very complex mathematical sets, a set can be as complex as anything that mathematics can create. Call it a universe. They actually call it a universe, the mathematicians, or a structure, and then describe this structure in another part of mathematics, logic, and then, because both are formal, and then you can have rigorously defined semantic links between them. There's even a symbol for it, namely this one in logic textbook, which is the modeling relationship. If you have such a statement here, a formula in formal logic, it models or is a, you could say denotes or describes correctly a set theoretic, a very complex set theoretic structure. Okay, how does that now relate to the real reality? Well, the mathematicians will shrug their shoulders and say, that's not our business. This is the part where the actual physical people come in and have to just accept this game and say, okay, well, let the mathematicians use reality, model reality with these complex structures. This will be complex enough to actually model that. And so the user of mathematics, of textbook logics, is charged to establish this link by its physical, mental operations and the things that this user does in the real world. It's not totally satisfactory, but it's how it is. Okay, so there are numerous examples, well, actually not numerous, there are a few instructive examples of such pairs where you have a descriptive mathematical formalism and some object universe, another part of mathematics that is able to give a very detailed and very rich structure. So one is the one that I just mentioned in formal logic. It's the best developed one. Then I would also say, I argue this in this paper, that probability distributions can be seen as descriptors of richer and more involved structured the probability spaces where the mapping is done by random variables. Then there is in computer science, the descriptive formalisms are the formalisms of computer scientists, digital computer scientists, programming languages, Turing machines, lambda calculus, and all the other equivalent ways to describe algorithms. And the models that is the current state-of-the-art way of modeling what programming languages do or what they mean is so-called domain theory. I will explain this in later slides because it's a central topic for me today. So keep this in mind. This thing, we will speak more about it. And then there is another way but it's hardly worked out and hardly understood as a semantic relationship, but I feel it could be expanded in this. Many neuroscientists and neuromorphic engineering people describe their physical systems with, let's say, with ODEs, differential equations, and they want to describe what's happening in these fine-grained differential equation systems on a qualitative level with qualitative phenomena like attractors, bifurcations, and other self-organizing phenomena. So these higher level descriptions, or the mathematicians would say the qualitative phenomena in, you could say, the numerical high precision systems. That could also be seen as a semantic connection, if you wish so. And for the general formal theory, we don't have anything yet. So to make things a bit more complex, the computer scientists also speak of semantics, but in a different way than the logicians do. And I'll just briefly mention, for them, the abstract descriptive format is typically program code or programming languages, but it could also be models of Turing machines or lambda calculus or some other equivalent formalism. So that's abstract mental stuff in the middle. And they want, for several purposes, have, you could say, object formalisms such that these things mean something more concrete elsewhere. And they speak of operational semantics when they want to map it to machines. And then they use state transition, discrete state transition formalisms to model the object universe. Sorry. When they want to model tasks, they normally use formal logics. And then, interestingly, the object formalism now becomes logic instead of what the logicians think is the object formalism for logic set theory. So they don't go that last step. So it's all very confusing. And finally, when they speak of denotational semantics, they want to have in a sense, that's not quite clear what they want to have, but it's the main business that they do in theoretical computer science. They want to have the most meaningful interpretation of what a program does, the essence of program code or a Turing machine. And what program code denotes, what it means. The purpose of doing this is to be able to, for instance, to say, okay, I here have a programming language A, a programming language B. I have a statement written down in language A, or a piece of code in that language. Do they do the same things? Do they mean the same thing? Is there a way to unify the discussion of code? Although they might use different input and output formats, for instance. So it's not mapping identical input to identical output, it's more general. And these questions are treated in so-called denotational semantics. Okay. Yeah, so, and these different sorts of semantics are also related to each other. And the modern textbook theory on computer science knows how to relate these things to each other. There's a very readable, very short intro to this in this paper by Leon Hornischer, whom I owe a lot. Okay, so back to our business. We are coming to the final slides. First of all, that's a reminder what I'm up to in what I hope to see developing. So some things we already have for such a general formal theory, namely, at the bottom, many formalisms for describing physical systems. Every physicist knows how to do this, but they have different ways. Then for the middle part, we also have a lot of proposals. In digital computing, there are very many equivalent ways to describe things, and they come in abstraction hierarchies. Today, I will skip this very interesting part. And on the top, we do not have very much. We do not know very well how to formalize tasks. Only the theoretical computer scientists can do this to a certain degree. We as neural neurocomputing people, we might also include tasks like learning tasks, which are not typical tasks for the digital people, as well as task specifications. But there might be many other sorts of tasks. For the object formalism, so these were the descriptive formalisms. For the object formalisms that we need for semantic theories, we have at the physical end, well, looking at the digital world, discrete state transition systems, or more generally, these probability spaces and these set theoretic structures that the logicians would use. At the top, we have again the same, but we don't even ask the question, except if we are digital computer scientists, when we would be using the set theoretic structures that they are using. And in the middle, for the object formalisms, we only have domains in classical computer science. And I will say a few words about domains next. So, reminder, we are talking about something that no one has a full sight and perspective on. So if you feel confused, that's the only correct way to feel. What we would need, in my feeling, is formalisms on these three levels that generalize what the digital people say and think in many ways. This is detailed in some of the works that are cited on the slides. But generally speaking, the digital world thinks of algorithms as an input-output mapping, whereas we should generalize this to interactive, ongoing, non-stationary, evolving thinking, where the computing system is interacting in an entrained way with the user. And to bind this all together in a mathematical way, I think we would be very well off if we could have a unified mathematical model, how to say, object universe model, a way to describe the semantic mapping target, namely what the things that we would be describing with descriptive languages here at the needed formal object model level. Okay, so, and I want to conclude with highlighting domains, which is a mathematical branch, domain theory, that probably is not very well known outside theoretical computer science. It has originated with Dana Scott technical paper in the 97 and now has grown to a textbook with 590 pages. It's a massive piece of mathematical theory, which is one branch, you could say, of set theory and of theory of ordered systems, of partial orders, that is very, very rich and expressive and can work and can give you abstract but very richly structured, you could say, realizations over which computing systems can be defined to do their computations. So it is in theoretical computer science the object world model. So I have only 40 seconds left, which means I can only give you a short intro into this. What is a domain? So a domain is a mathematical structure. It's a partial order which relates to a computing process as follows. So this is very shortcut. Many details are missing. So the idea is that if physical computing goes on, the states of the physical machine, each of them means something. What does it mean to mean something? They carry information. Well, at least you want to be able to say this is more rich in information than the other. So you want to be able to have a partial order on these pieces of information that you can extract from states of a computing machine. So the things that can happen during computation can be ordered in a partial order, where if it's higher up in the order, it means it's richer information. It contains more information. Here's a picture of this. And the domain theory tries to come to terms with continuity conditions in these. That is, if you have more and more and more information about something, if the computation goes on and on and on and on and creates more and more information, does this converge to something? So adding topological notions of convergence to this whole picture gives you domain theory. So domain theory is basically theory that gives you very richly structured mathematical systems, partial orders, whose nodes can be immensely rich. These can be data structures, logical formulas, even sets, even infinite sets of each of these could themselves be domains. So it can be breathtakingly rich objects, each of these dots. They are related by becoming richer and richer, and you can have topological additional information about that tells you when you approximate something by letting, let's say, a computation going on, which is also, of course, relevant for neuromorphic computing very directly, because we all know how important it is to understand better the effects of having finite precision or even imprecise state information. Okay, my time is up, and therefore, so you don't see this, but I have a very strong warning sign looking at me here and therefore I will cut close and just say, I think thinking about domains is a good starting point to think about a general formal theory. At least it's a necessary, something like this is a necessary thing that we have to develop. And I owe a lot to Levin Hornischer, with whom I have started to collaborate, who just, I wanted to give you at the last slide, which is too long now, I will just say that it is on the last slide and it's written in these papers. In his PhD thesis, just the title, let this sink in, Dynamical Systems via Domains, so he's a logician / computer scientist / philosopher, toward a unified foundation of symbolic and non-symbolic computation. I think this is the way, it's one possible way to go, and where his work shows how one can at least start to connect these very powerful tools that the logicians / computer scientists have developed to understand the meaning of computing, but connect this to ongoing, continuous time processes, where you have a physical system. He connects this to ergodic theory of physical systems, and interprets them with the tools of domain theory. It's not easy stuff to understand, but I would say that's the way to go ultimately. So unfortunately, all I can say is I had nice slides for that as well. This is the first time I give this particular talk. All the slides are new, therefore I didn't have full control over the time, the summary. So I think we need a general formal theory to advance our field and other fields as well. It's not only neuromorphic computing, it would be the general theory of computing. This is not meaning that there's a little simple trick like inventing the Turing machine for another sort of Turing machine and we have it. It will be a network of interrelated theories. Among others, we need to be modeling task machines and the computing processes with different formalisms. And interrelating these formalisms means we also need sub-theories, ways to discuss semantic relationships. So that's roughly it. And all I can say is I don't have more answers. I'm working at this myself very much. I'm very happy that Levin Hornischer helps me. I have only started to dig into this myself. And my basic feeling is that the neuromorphic world would have benefits from talking more with the theoretical computer scientists who know about this logic stuff, but it's very difficult to talk with them because they have no reason to talk with us, unfortunately. They have their own very rich world of rewards and projects and problems, so they don't need our problems on top. And that's really an experience that I make. I'm so happy that at least one or two of them, like Levin, have started to cross the road and shake hands with us and try to use their methods in our world. Okay. Yeah, that was it.